Hi, I'm Anamika. I work at SLAC National Accelerator Laboratory, which is a national lab run by Stanford University. Most of this work was done at Stanford and the synchrotron facility at SLAC. So my talk is going to be about extraction of critical minerals from hydraulic fraction waste materials and possibly sourcing that and causing possible environmental impact mitigation. So the objective of this work was to see if these sources like oil, gas, waste streams are a viable source of critical minerals at all. And then, once we identify or see any critical minerals, see and correlate these critical minerals with different sedimentological phases. And after that, identify the phases or like the chemical speciation of these critical minerals so that we can do targeted extraction on these. And the final step is the targeted extraction techniques and possibly which we are thinking of doing next is in situ extraction of minerals. So we're seeing the periodic table again. So I don't think I need to talk too much about the significance of critical minerals in this particular audience. We need it for different electronics, renewable energy, electric vehicles, and currently we do not have enough critical minerals available for a complete green energy transition. And most of the times, the traditional mining can be not very environmental friendly, and if we do these kind of materials where extractions where we can utilize the waste materials, it could be a good solution to that as well. So why am I looking at this particular source? Why unconventional oil, gas wells? First of all, there are thousands of wells drilled every year. And currently, all of the materials that come out of it are purely waste material, which are landfilled. And each well is several miles long because it goes vertically and then it goes horizontally, so it's several miles long. And since it's so long, it covers diverse rock types, like different kinds of lithologies. So with all of this, it encompasses to be a huge volume of rock waste, which is entirely being landfilled at this point. So if we're able to do this, we can do two things. First, by taking the minerals out of it, how much ever we can, we'll be potentially reducing the toxicity of the materials that go into the landfill. And the other one, we can possibly bring in another supply chain for these materials. So coming into the project, so all my samples were collected by our collaborators who were from West Texas. So all the samples were from Permian Basin. So the image on the right-hand side shows the different basins. So the samples that I got were specifically from the right-hand side of the Permian Basin, which is the Midland Basin. And the image on the left shows the cross-section across these different basins. So a little more information about the samples. So I was given samples by our collaborators from 4 different exploratory wells in the Permian Basin. And these wells varied in their depths from about 6,000 to 12,000 feet. And samples were taken at every 30 feet for the wells that were shallower, that is 6,000 feet, and every 60 feet for the wells that were a bit more deeper. So in total, I had more than 600 samples to work with. Our collaborators were more than generous with this. It was great, but also a lot of work. So how did we approach this project? So doing these many samples and analyzing them is not easy. So first, that's how I received all my samples in different small vials. And the bottom part is like the solid part with like crushed rock. And on top, some of the samples had a supernatant liquid. So we separated that out and analyzed that separately. And I'll not be talking too much about that in this talk. I'll be concentrating on the solid part that was obtained on the bottom. So first, these materials were centrifuged and separated and ground and dried. And these materials, all of these samples were pre-screened using XRD and XRF. X-ray diffraction, which is XRD for understanding the mineral composition, and X-ray fluorescence measurement, bulk X-ray fluorescence measurements for getting general elemental composition in these materials. So once we got the elements and mineralogy of these samples, we down-selected which samples we were interested in. And then is when we went and did synchrotron analysis, different techniques like X-ray absorption spectroscopy, X-ray fluorescence mapping, and micro-XAS on those samples to identify what species or like what compound these minerals are existing as, so that we can go to the next step, which is the sequential chemical extraction, or trying to see how to extract these materials, and finally acid digestion. So this is a slide showing the X-ray diffraction and different sedimentological units across the 4 different wells that we had. So as you can see, different samples from the wells were collected at different depths. So this is how we got the samples. So that's what it is. It shows a lot of variability with respect to the sedimentological units in these wells. That's important because I'll be coming to that point later. So first, when I was trying to do X-ray fluorescence measurements on these samples, it was not, the X-ray fluorescence instrument was not optimized for these many critical minerals. So first, I had to optimize the instrument by taking NIST standard reference material and spiking those with different concentration of the different solutions. And 20 new elements were added to the list. And after that, I will go to the results of the sample, results of this analysis. So the first one, the X-ray fluorescence screening, which was the elemental mapping, sort of, not mapping, elemental analysis. So this would give the elemental composition of the sample. So I have a representative sample on the right-hand side. I don't have all the plots because it'll be too much. So what we saw was there were some elements like titanium and other transition metal elements that were consistently present, and these aligned with silicon and aluminum throughout the samples. And other transition metals like vanadium were seen to be present in exceptionally high concentration in some well, like in most of the wells, and very high concentration in one of the wells. If you see the plot for vanadium, you can see that it skyrockets to about weight percentage level of vanadium after it hits the 10,000 feet level. And after this, an arbitrary amount of limit of 100 ppm was chosen for the rest of the synchrotron analysis. So this is a table summarizing different critical minerals that we saw in all 4 different wells. So titanium we saw in a few thousand ppms, vanadium in a few hundred ppms, and in one well, the well number 3, you can see in the red highlighted box that it was present in about 30,000 ppm, which is weight percentage level. And zinc was present in 100 to 600 ppm, and in one particular well, only in one unit. It was not throughout the well. It was only just one section. We saw a few, like 100 ppm level of silver, indium, and yttrium as well. And all the concentrations are in ppm here. So coming to the synchrotron-based analysis, so X-ray fluorescence elemental mapping is a technique that you can do a mapping of the entire surface of your sample and see what elements are present in them. So we can, it can be useful with respect to doing elemental association and how they're associated and how they're distributed. So here we can see that the titanium and vanadium were not very correlated, so that would require a potentially different extraction techniques. And some elements had high correlation, like molybdenum and sulfur were very much correlated, so possibly they exist as sulfides. Zirconium and silicon were correlated as well, so probably silicates. And after doing this, I also did X-ray absorption spectroscopy and synchrotron for titanium, vanadium, zinc, and manganese for understanding the speciation of these materials. So the only reason I did only for these 4 materials is due to the limitation of timing. But if I had more time on this project, I would have been able to do more. That would have given more information. But this is what we have at this point. So going to the titanium X-ray absorption spectra. So X-ray absorption spectra are the spectroscopy that's using the synchrotron, and how we can understand the data from it is it's a very fingerprint sort of a spectra for each element, and it depends on the oxidation state and the environment of each element present in your sample. So it's a very fingerprint analysis. So if you look at the left side image is the image of my sample, the spectra that was collected, and on the right-hand side is a reference image. So what we were able to see was there was extreme amount of consistency present across different wells and also within the same well at different depths. This was interesting to me because as you had seen in the previous image where with the sedimentological information, it is pretty diverse. So the Permian Basin being a sedimentological basin, I was expecting that there would be a different composition, or a different speciation of these elements at different depths. But that's not how we are seeing it. We're seeing that it's pretty consistent. And comparing our data to the reference spectra, it looks like titanium is existing as a mixture of rutile and anatase. And it's either of the, whether it's rutile or anatase, it's still titanium dioxide, and there is a very established technique for extraction of these materials known as Kroll process. Going to the vanadium spectra, again, the image on the left is the spectra that was collected at SSRL, and on the right is the data from reference. And since vanadium can exist in different oxidation states, we first had to make sure that there was no beam damage. Beam damage is changing of the oxidation state of the material when it's exposed to very high X-rays. So we had to make sure that that was not happening, and it was not. And we also had huge amount of barium in our sample, about 30,000 ppm in some samples, which caused a lot of it affected the collection of titanium and vanadium spectra because their X-ray energies are very close to each other. And even in vanadium, we were able to see that there was high consistency among the samples in the same well and also in different wells. And by looking at the reference, what we can see is it looks like it is vanadium-3, but we're not yet sure what exactly it is. Vanadium carbonate, or it's vanadium-3 is what it looks like from the reference on the bottom. So zinc XAS, also a similar story, and from comparing to the reference spectra, it looks like it is zinc sulfide. And this we were able to confirm if we get in the XAS spectra, how much ever far we are able to get in our data. If we get a good amount of data, we can do more analysis on it called XAF analysis to confirm the structure. So in this, we were able to do that, and we were able to confirm that it was zinc sulfide indeed. And for manganese, it looks like it is manganese carbonate. And after we got the speciation, we did the sequential chemical extraction, which you may be familiar with, which is treating your samples with increasingly stronger chemical extractants to see how much you can extract in each step. And these are the steps as it's mentioned here. So I'll summarize the results, the interesting result of the sequential chemical extraction that I got. So vanadium seems to be extractable with very mild reagents. So I was able to get about 90% of the vanadium present in the samples with just magnesium chloride solution, which is an exchangeable solution, which is great because you don't have to use very harsh chemicals. And for titanium, looks like it's a step number 3, which is also acetic acid mixed solution that was able to extract a good amount. And the others, it was some amount in each step. So concluding the talk, the unconventional oil gas wastes offer a potential supply stream for critical minerals, at least for the elements that we were able to find. And calibrating the XRF for these critical minerals reduces the screening time and minimizes the chemical waste that would be produced with acid digestion if we had to do for all samples. And heavier transition metals were generally seen to increase as it went down in the depth. And even though we wanted to see rare earth elements in our samples, we did not really see much. So Permian Basin, at least the area that we got our samples from, looks like it's not a great spot to find rare earth elements. And finding high concentration of certain critical minerals like vanadium could potentially suggest that we could do in situ extractions over there, and consistent phases were identified for some elements, and majority of vanadium seems to be extractable with mild reagents. And I thank everyone who helped me with this project, and the project was funded by DOE, Fossil Energy and Carbon Management. Thank you.